What if everything you've ever seen, touched, or imagined is just a tiny wrinkle in something that has no edge, no end, no boundary whatsoever? Now here's the uncomfortable part, and how would you even know? Welcome to the channel, where we don't just hand you answers, we hand you better questions. Today we're diving into one of the most mind-bending ideas in all of physics, the size of the universe itself. And I promise you, if you stick around till the end, your intuition about space, infinity, and reality is going to get a very satisfying shake-up. If that's the kind of thinking that excites you, hit subscribe, because this is exactly what we do here. Now let's start with something that sounds simple. Infinity. You've heard the word. Maybe you've even used it. The universe is infinite. People say it casually, like it settles something, like saying infinite is the end of the conversation. But here's the thing, and this is what I find so delicious about physics. The moment you actually sit down with infinity and try to work with it, really work with it, it stops behaving. It gets slippery. It starts causing trouble. So let's cause some trouble together. Start with something familiar. Imagine you're a child and someone asks you, "What's the biggest number?" And you think, well, whatever number they say, I'll just add one. A million and one, a billion and one. You can always go further. So numbers don't stop. They just keep going. That feels like infinity, right? An endless staircase with no top floor. Fine. Now here's where it gets interesting. What if I told you there are different sizes of infinity? Not bigger and smaller in the way a cat is smaller than a horse, but genuinely, mathematically, provably different magnitudes of infinite. The infinity of whole numbers, 1, 2, 3, 4, is actually a smaller kind of infinity than the infinity of all decimal numbers between just 0 and 1. Think about that. An infinity contained inside a single inch on a number line is larger than the infinity of all counting numbers stretching forever. Now your intuition is already complaining. Good. That's exactly the right reaction, because infinity doesn't work like a normal number. You can't add to it, divide it, or reason about it the way you reason about 6 apples or 12 meters. The moment you treat infinity like a quantity, like something you can measure, the mathematics starts handing you nonsense. And physics noticed this problem. In the early 20th century, physicists were building the equations that describe how light and matter interact, what we now call quantum electrodynamics. Beautiful theory, extraordinarily precise, the most accurate physical theory ever constructed, in fact. But when they sat down and calculated certain quantities, the energy of an electron, for instance, the math kept returning the same embarrassing answer. Infinity. Not a big number, not an approximation, a literal, useless, infinite result. Now you might think, well, maybe the universe is infinite in some deep sense, and the equations are just telling us that. But that's not how a physicist thinks. When your answer is infinity, that's not a discovery. That's a signal. It means your theory is incomplete. It means you've pushed your equations somewhere they were never meant to go, and they've stopped telling you something true about the world. It's like asking your car's GPS for directions to the moon. It won't give you a route. Not because the moon doesn't exist, but because the tool has hit the edge of what it was built to handle. So here's the deeper idea. Physics isn't just about what is. It's fundamentally about what we can measure, test, and verify. And infinity, by its very nature, is something you can never finish measuring. You cannot travel an infinite distance and come back to report on it. You cannot count to infinity and check the result. You cannot build an experiment whose outcome is literally boundless. This is why serious physicists, not the casual ones but the careful ones, treat the appearance of infinity in their equations not as a window into cosmic truth, but as a red flag, a warning that something in the model needs revisiting. And when we apply this exact same thinking to the universe itself, when we ask, is the universe actually infinite? We have to be honest about something uncomfortable. We don't know. And more importantly, we might never know if we keep assuming infinity is a satisfying answer rather than a question in disguise. Because here's the real trouble with infinity. It feels like an answer. It sounds grand and vast and complete. But in physics, the most dangerous ideas are the ones that feel like answers, while quietly preventing you from asking better questions. The universe may not be infinite. And the reason we suspect that, the reason careful physics nudges us in that direction, is exactly what we're going to explore together in this video. So stay with me, because it gets much more interesting from here. Let me ask you something that sounds simple but absolutely isn't. When someone tells you the universe is expanding, and it is, we know this, it's one of the most well-confirmed facts in all of modern physics, what's the first question that pops into your head? I'll bet it's this one. Expanding into what exactly? And honestly, That's a perfect question. That's the question a genuinely curious person asks. So let's not brush it aside the way textbooks sometimes do. Let's actually sit with it, because the answer is one of the strangest and most beautiful ideas physics has ever produced. First, let's establish what we actually know. In 1929, an astronomer named Edwin Hubble made a remarkable observation. Galaxies, other islands of stars scattered across the cosmos, were moving away from us. Not just a few of them, almost all of them. And the further away a galaxy was, the faster it appeared to be receding. Now, the instinctive interpretation is, we must be at the center, and everything is flying outward from us, like debris from an explosion. But that's not what's happening. And here's where you need a thought experiment. Imagine a loaf of raisin bread rising in an oven. The dough is expanding. The raisins, let's say they're galaxies, are embedded in the dough. As the bread rises, every raisin moves away from every other raisin, not because the raisins are flying through the dough, but because the dough itself is expanding. Now, and this is crucial, if you were sitting on one particular raisin, you'd look around and see every other raisin moving away from you. You'd feel like the center, but so would every other raisin. There is no center. There is no edge. The expansion is happening everywhere, simultaneously, in the fabric itself. That fabric is space. The universe isn't expanding into something. Space itself is stretching, growing. The distances between galaxies are increasing, not because galaxies are moving through space, but because the space between them is genuinely, physically getting larger. This is not a metaphor. This is what the equations of general relativity actually describe. And it's been confirmed through decades of observation. But now your question gets sharper, and rightly so. If space is expanding, if the fabric itself is stretching, then what's outside the fabric? What's on the other side of the bread, so to speak? And here's where I have to be honest with you. The way physics demands honesty. We don't know. And more precisely, the question may not be physically meaningful. Here's why. Everything we can ever observe, test, or measure exists within space and time. Our instruments are inside the universe. Our light, our signals, our entire capacity to gather information. All of it is bound by the same expanding fabric. There is no observation post outside the universe from which we could look back and say, ah yes, it's expanding into that. It's a little like asking what's north of the North Pole. The question sounds sensible, but the coordinate system that gives north its meaning simply doesn't extend beyond that point. The question isn't unanswered, it's malformed. Now here's the deeper implication, and this is where it connects directly to our central question. If the universe is expanding, it was once smaller. Wind the clock back far enough, and all the matter and energy we can observe was compressed into an extraordinarily hot, dense state. We call the moment it began expanding the Big Bang. And listen carefully here. The Big Bang was not an explosion in space. It was an explosion of space. Space itself began. Time itself began. There was no before. Not in any meaningful physical sense, because time as we understand it emerged with the universe. This matters enormously, because if space had a beginning, if it started from a finite state and has been expanding for a finite amount of time, then the universe we can possibly access, the universe that is real in terms of observable physics, is not infinite. It is vast beyond imagination. But vast is not the same as infinite. And that distinction between unimaginably large and truly without limit is exactly what the next section is going to crack open, because it turns out the shape of space itself holds the answer, and the shape is far stranger than you might expect. Let me tell you something that took humanity an embarrassingly long time to figure out. The rules of geometry you learned in school, flat surfaces, straight lines, angles in a triangle adding up to exactly 180 degrees, those rules are not laws of the universe. They're laws of flat surfaces. And the universe, it turns out, is not obligated to be flat. That sounds abstract. So let's make it concrete. Start with something you can hold in your hands. Take a globe, a regular spherical globe of the Earth. Now draw a triangle on it. Start at the North Pole. Draw a line straight down to the equator. Now turn 90 degrees and walk along the equator for a quarter of the way around. Then draw a straight line back up to the North Pole. You've just drawn a triangle. 3 straight lines, 3 corners. Now measure the angles. Each corner at the equator is 90 degrees. The angle at the North Pole, depending on how far you walked, adds something more. Add it all up. Your triangle's angles sum to more than 180 degrees. On a flat surface that's impossible, On a curved surface, it's not only possible, it's inevitable. The geometry changes because the surface itself has a different shape. This was the radical insight that a mathematician named Bernhard Riemann developed in the 19th century, long before anyone applied it to the cosmos. Geometry isn't fixed. It depends on the curvature of the space you're working in, and different curvatures produce entirely different rules. Now, here's where Einstein enters the story. When Einstein developed general relativity, he took Riemann's mathematics and did something breathtaking with it. He proposed that space and time, together as spacetime, isn't a rigid, flat backdrop against which the universe plays out. It's a dynamic, flexible structure. And mass and energy don't just sit in space-time, they curve it. Think of a heavy bowling ball placed on a stretched rubber sheet. The sheet dips and curves around the ball. A marble rolled nearby doesn't travel in a straight line. It curves toward the bowling ball, following the contour of the sheet. That curving path is what we call gravity. Now, this is an analogy, and like all analogies, it has limits. The rubber sheet curves into a third dimension you can see. Real space-time doesn't curve into anything visible. It curves within itself. But the mathematical structure is identical. Mass curves space. Curved space tells matter how to move. That's gravity, not a force reaching across empty space. A curvature in the geometry of space-time itself. So what does this mean for the universe as a whole? Just as Earth's surface has a global shape, a sphere, the universe itself has a global geometry, a shape. And that shape is determined by how much mass and energy exist within it, spread across the whole cosmos. Physicists describe three possible outcomes. If the universe contains more than a certain critical density of matter and energy, gravity wins. Space curves back on itself, like the surface of a sphere. The universe is finite and closed. You could theoretically travel in a straight line and eventually return to where you started, just as sailing straight on Earth eventually brings you home. If the universe contains less than that critical density, space curves outward like a saddle, curving away in all directions simultaneously. This geometry is open and potentially infinite, and if the universe hits exactly the critical density, a razor's edge balance, space is flat, infinite, and geometrically ordinary. Now here's what our best measurements actually say. The universe appears to be remarkably, almost suspiciously close to flat. Data from the cosmic microwave background, the faint afterglow of the early universe, a kind of baby photo of the cosmos, suggests the curvature is either zero or extremely close to it. But here's the thing, close to flat is not the same as perfectly flat, and even a tiny curvature, applied across the staggering scale of the universe, could mean the cosmos curves back on itself so gradually that we simply cannot detect it yet. We might be living on the cosmic equivalent of an ant on a vast sphere, perfectly convinced the surface is flat because we haven't walked far enough to notice the curve. And that's precisely why the next section matters so much, because there's a hard limit on how far we can see, a horizon, and what lies beyond it, whether space curves, closes, or continues forever, is a question physics is only beginning to honestly confront. Let me start with a question that seems almost too simple to be interesting. Why can you only see as far as the horizon? Stand on a beach, look out at the ocean. Ships disappear over the edge at a certain distance, not because they vanished, not because the ocean ends there, but because the Earth curves away from you. The horizon isn't the edge of the world, it's the edge of your view from where you're standing. Now hold that thought, because the universe has a horizon too, and understanding it changes everything about how we think of cosmic infinity. Here's the setup. Light travels fast, blindingly, almost incomprehensibly fast, 300,000 kilometers every second. Nothing in the universe moves faster. That's not a practical limitation. It's a deep law of nature. But fast is not the same as instantaneous. Light takes time to travel. The light reaching your eyes right now from the sun left 8 minutes ago. The light arriving from the nearest star beyond our sun left over 4 years ago. When astronomers point their telescopes at distant galaxies, they aren't seeing those galaxies as they are today. They're seeing them as they were millions, sometimes billions of years in the past. Looking out into space is literally looking back in time. Now here's where it gets profound. The universe has a finite age. Our best measurements put it at approximately 13.8 billion years. That number is not a guess. It's derived from multiple independent lines of evidence, all converging on the same answer. So light has had exactly 13.8 billion years to travel toward us since the universe began. That means there is a maximum distance from which any light could possibly have reached us by now. A sphere centered on us, surrounding us in every direction, beyond which no signal, no information, no light of any kind has had time to arrive. That sphere is called the observable universe, and its edge is our cosmic horizon. Now you might think this horizon sits 13.8 billion light-years away, 1 light-year per year of cosmic age. Straightforward enough. But here's where expansion complicates things beautifully. Remember our expanding universe from earlier. While light has been traveling toward us, space itself has been stretching. The distant regions that emitted that ancient light have been carried further away by the expansion of space during the billions of years the light spent in transit. It's like trying to walk towards someone on a moving walkway that's carrying them in the opposite direction. You still reach them eventually, but the journey covers more distance than you'd expect. Because of this expansion, the observable universe extends not 13.8 billion light-years in every direction, but closer to 46 billion light-years. That's the current distance to our cosmic horizon, accounting for all the stretching that happened along the way. 46 billion light-years in every direction, an almost insultingly vast sphere of observable reality, and yet a sphere with an edge. Now let's be very careful here, because this is where people often get confused. The cosmic horizon is not the edge of the universe. It is the edge of our universe, the portion we can observe, the portion with which we can ever exchange information. What lies beyond it may be more space, more galaxies, more matter behaving by the same physical laws. We simply cannot know, because no light from beyond that horizon has had time to reach us. Not yet, perhaps not ever, if the expansion continues accelerating, which current evidence suggests it is. It's a little like living in a fog so thick that you can only see 20 feet in every direction. You can map those 20 feet beautifully and precisely, but you cannot honestly make claims about what lies beyond the fog, except by inference and educated reasoning. And here's the deeply important consequence for our central question. When someone asks, "Is the universe infinite?" they're often unknowingly asking about something that lies beyond our observable horizon, beyond the boundary of what physics, by its very nature, can directly test or verify. This isn't a failure of our instruments. It isn't a temporary problem we'll solve with a bigger telescope. It is a fundamental, principled boundary on empirical knowledge. The horizon is real, the limitation is real, and yet physics doesn't surrender at the horizon. It reasons carefully beyond it, because the shape of space, the geometry we explored in our last section, carries clues. Clues that point, quietly but insistently, toward something remarkable, a universe that may be finite, bounded, complete, without having any edge at all. We've arrived at the most beautiful idea in this entire video, and I want you to really sit with it, because this one is the kind of idea that, once it settles into your mind properly, permanently changes the way you think about space, about reality, about the very meaning of the word edge. Here it is, stated plainly. The universe may be finite in size, containing a measurable, specific amount of space, and yet have absolutely no boundary, no wall, no edge, no place where space simply stops and something else begins. Your intuition is probably objecting right now. Good. Let's walk through it carefully. Start with something familiar. Again, our sphere. Take the surface of the Earth. It has a finite area. You could, in principle, measure every square kilometer of it and arrive at a total number. It is not infinite. It does not go on forever. And yet, find me the edge. Walk in any direction, as far as you like, for as long as you like. You will never fall off. You will never hit a wall. You will never reach a sign that says surface ends here. The surface of a sphere is finite, but it is also seamlessly, perfectly continuous. No edges, no boundaries, no seams. Now, then, this is the conceptual leap. Imagine that same property, not on a two-dimensional surface, but applied to three-dimensional space itself. Imagine a universe where, if you traveled in any direction in a perfectly straight line for long enough, you would eventually return to your starting point. Not because you turned around, not because space looped you back artificially, but because the geometry of space itself curves gently and consistently back on itself, just as the surface of a sphere curves back on itself, only in one higher dimension. That universe would be finite. It would contain a specific, measurable volume of space, and it would have no edge whatsoever. This isn't science fiction. This is serious physics. The mathematical framework for exactly this kind of space has existed since Riemann's work in the 19th century. Einstein's general relativity not only permits it, it predicts that the global shape of the universe is determined by its energy content, and a sufficiently dense universe curves closed exactly like this. Physicists call it a closed universe, and the three-dimensional version of our spherical surface analogy is called a three-sphere, a shape that exists in four spatial dimensions, impossible to visualize directly, but entirely describable mathematically and physically meaningful. You don't need to visualize it. You need to understand what it implies. It implies that space can be self-contained, complete, whole, with no need for anything outside it, no requirement for an edge, no logical necessity for something beyond. Now here's the question you should be asking. If this is true, if the universe curves back on itself, why haven't we noticed? Why hasn't light traveled all the way around and returned to us from the opposite direction? Two reasons. First, the universe may simply be too large. Even if it curves closed, the circumference of that closure might be so vastly greater than our observable horizon that the light completing the journey hasn't arrived yet. We'd be like an ant on a basketball, convinced the surface is flat because the ant hasn't walked far enough to detect any curvature. Second, and our measurements confirm this, the universe appears extraordinarily close to flat on the scales we can observe. The curvature, if it exists, is so subtle, so gentle across the observable universe, that our instruments sit right at the edge of detecting it, close to flat, but not necessarily perfectly flat. And that distinction carries everything. So here is where we land, honestly, carefully, the way physics demands. We do not know with certainty whether the universe is finite or infinite. Anyone who tells you otherwise with complete confidence is overstepping what the evidence actually says. But we know this: a finite, unbounded universe is not only possible, it is physically motivated, mathematically consistent, and entirely compatible with everything we observe. The universe may be like the surface of an enormous sphere, vast beyond any human scale of imagination, curving so gently that no measurement we've yet made can detect the bend, containing everything that exists, every galaxy, every particle, every moment of time since the beginning, and yet complete, finite, edgeless, whole, not infinite, just everything. And somehow, that's even more remarkable. So, let's bring it all home. We started with a word that sounds like an answer but behaves like a problem: infinity. And we discovered that the moment physics actually tries to work with infinity, to calculate it, measure it, verify it, it starts handing back warnings, red flags, results that tell us we've pushed our thinking somewhere it no longer reflects reality. Then we looked outward. We saw a universe that is expanding, not exploding into pre-existing empty space, but stretching the very fabric of space itself. A universe whose expansion traces back to a beginning, a finite starting point, a moment before which the word before loses its meaning entirely. We looked at the shape of that space and discovered that geometry itself is not fixed, that space can curve, that a universe can be closed and self-contained, the way a sphere's surface is closed and self-contained, with no center, no edge, and no outside, finite in volume, boundless in experience. We confronted the horizon, that humbling, fundamental boundary beyond which no light has had time to reach us. And we were honest about what that means. Not just that we haven't looked far enough, but that there exists a principled physical limit on what any observation, any telescope, any instrument can ever tell us about what lies beyond. And finally, we arrived at the most quietly revolutionary idea of all, that the universe may be finite without having an edge, complete without being confined. Everything that exists, wrapped into a geometry so vast and so gently curved that no journey we could take would ever reveal the seam. Now here's what I want to leave you with. None of this is settled. Physics does not pretend otherwise. The universe may be infinite. The evidence doesn't conclusively rule it out. But the honest, careful, evidence-respecting position is this: we have no confirmed observation that requires infinity. We have no measurement that demands it. What we have instead are strong theoretical motivations, geometric possibilities, and the persistent, quietly urgent lesson that infinity in physics is almost never a final answer. It is almost always a question wearing a costume. The universe may not be infinite, and the reasons to suspect that, drawn from expansion, from curvature, from horizons, from the fundamental discipline of only claiming what observation can support, those reasons are serious. They are worth understanding. They are worth sitting with. Because here's the thing about physics done right. It doesn't just tell you facts. It teaches you how to think about facts, how to hold an idea firmly enough to examine it and loosely enough to revise it, how to be genuinely comfortable saying, "We don't know yet," while continuing to reason carefully towards something better. That's not a weakness. That's the whole enterprise. That's what makes it endlessly, stubbornly, beautifully interesting. And that's exactly what this channel is about. Not handing you conclusions wrapped in false confidence, but walking through the real ideas, the strange ones, the counterintuitive ones, the ones that make your intuition complain before your understanding catches up, with clarity, with care, and with the deep respect that curious people deserve. If that's the kind of physics content you want more of, and I genuinely hope it is, then subscribing to this channel is the simplest thing you can do right now. Hit the button. Turn on notifications if you want to make sure you don't miss what's coming next, because we're just getting started. There are more ideas where these came from. Ideas about time, about quantum reality, about the strange behavior of light and matter at scales both unimaginably small and cosmically vast. Ideas that will challenge what you think you know and leave you, I promise, with something far more interesting than certainty. Curiosity is the engine. Clarity is the goal. We'll see you in the next one. And that's it. That's the idea. The whole strange, wonderful, slightly unsettling thing, laid out as honestly as I know how to lay it out. I want to say something genuinely, not as a formality at the end of a video, but because I actually mean it. Thank you for watching. Not just for pressing play, but for staying, for thinking along, for letting yourself sit with ideas that don't resolve neatly, that don't hand you a tidy answer and send you on your way. That takes a certain kind of intellectual patience, and it's rarer than it should be. You know, the best thing about questions like these, about the size of the universe, the shape of space, the honest limits of what we can know, is that they don't leave you feeling smaller. They leave you feeling connected to something genuinely vast and genuinely mysterious. And there's a quiet joy in that, if you let yourself feel it. I feel it every time I sit down to think through one of these ideas. I hope some of that came through today. If anything in this video sparked a question, something you want to push on, something that didn't quite sit right, something you want to understand more deeply, that's not a problem. That's the whole point. That's exactly what's supposed to happen. Physics isn't a destination, it's a direction, and it's always good to have company on the way, so thank you, genuinely, for your time, your curiosity, and your willingness to think carefully about something difficult. I'll see you in the next video.